So thanks everyone for attending. Today, MatSE is celebrating women scientists and inventors as part of Women's History Month. I do want to acknowledge that some of us are participating in this event as allies. And with that, I want to hand it over to Enrique for some opening remarks.
Thank you, Wes. And I appreciate many thanks to Wes for putting this event together and organizing all of us to help us highlight a variety of different women's scientists, inventors, and educators, and so on. I'd like to just very briefly, before we get started, just say a couple words about last year's event. Just to, I guess, highlight the celebration that we did in 2021 that included a variety of folks. I have 3 pages of this, so let me just go through it really quickly, including Helen McGaw, our very own from Penn State, Danielle Rice-Snyder-Hickey, Jane Cook, and again, our very own Joan Redwing, also at Penn State, UU2, our very own Suzanne Moni from Penn State, Carletta Chief, Elizabeth Cup from Penn State, Susan Troller-McKinstry from Penn State. And in the next page, we have a variety of other folks, including Amy Robinson from Penn State, Rosalind Franklin, Franz Cordova, Allison Beasy from Penn State, Patricia Thiel, Maria Molina Higgins from Penn State, Maria Curie, Kristen Dreyer from Penn State, and Tiffany Matthews. And one more slide, please. Emily Emmett Norther, Yara Hasegawa from Penn State, Susan Sinot from Penn State, Dorothy Hodgins, Nasima Lem from Penn State, Xiaotan Li, Catherine Johnson, Mildred Dresselhaus, and Michelle Simmons. So there's a variety of folks that have contributed to material science and science in general, made various accomplishments from everything in terms of ceramics, experts in ferroelectrics, experts in terms of mathematics, worked on things like space programs, et cetera, et cetera. It's been a wonderful group to be able to highlight last year. And if you want to learn more about it, we have some links at the bottom. We have a webpage where you can find the links to a couple of videos of last year's events, which are at the very bottom there. And if you're interested in learning more about any of these folks, I encourage you to check it out. But for this year's event, let me hand it back to Wes.
So we'll just go ahead and launch right in. So Nancy, you want to go ahead?
Yes, hi everyone. So for today's Women History Month webinar, I'd like to spotlight Dr. Grace Hopper. Just as a brief overview of her early life, she was born on December 1906 in New York City. She got her bachelor's in mathematics and physics from Vassar College, as well as her master's and PhD in mathematics from Yale. She also taught mathematics as a professor at Vassar College for 12 years until 1943. So in 1943, during World War II, she was sworn into the Navy as a member of the Navy Waves program, or the Navy Women Accepted for Voluntary Emergency Services program. And she was assigned to the Bureau of Ships Computation Project at Harvard, where she worked on the Mark I computer. And so this computer was an electromechanical computer used for computations and then analytics in the during World War II. And so after World War II, she continued to serve in the Navy, and she stayed at the Harvard Computation Lab and worked on the Mark II computer, where she actually discovered a moth that was stuck in the computer. And that's actually where we get the term computer bug from, because the bug was not allowing the computer to work. And so we've popularized that term for today's bugs. So I just thought that was a fun fact. And then Dr. Hopper, she actually retired 3 times, but was recalled into active duty twice. And by the time she retired, she achieved the rank of Rear Admiral, where at that time there was only a few female admirals. So she was one of the few. And during her retirement ceremony, she was awarded the Defense Distinguished Service Medal, which is the highest non-combat decoration award that's given by the Department of Defense. And she was also a distinguished fellow of the British Computer Society. She was actually the first woman, as well as the first American, to become a distinguished fellow. Next slide, please. And so just to talk a little bit more about her inventions, she joined the Eckhart-Mauchly Computer Corporation in 1949, where she helped develop the UNIVAC-1, which is the first large-scale electronic computer to be available on the market. And she also invented the first computer compiler, which was called the A0 compiler, as well as helped develop Mathematic, Flowmatic, which are two other compilers. She co-developed the COBOL program, which is one of the earliest computer languages with syntax that's similar to speaking English. So rather than coding in symbols, it was more like just speaking English. And then she was also the first director of the automatic programming department at this corporation. She also helped develop standards to test the computer systems as well as components for programming languages such as COBOL and Fortran. And one quote from Dr. Harper that I like to share is, "The most damaging phrase in the language is, 'It's always been done that way.'" And I just found this quote very inspiring and really a reflection of Dr. Harper's life, because she was constantly developing and inventing and really advancing her field of computational sciences, which we use very frequently now in material science and engineering. And yeah, that's it. Thank you.
Thank you. All right, let's move ahead.
Hello, my name is Christopher, and today for my spotlight, I wanted to nominate one of our professors here at Penn State, Dr. Andrea Argues. So she was originally born in Venezuela and then later got her bachelor's and her master's in mechanical engineering at the University of Texas in Rio Grande, with her specialty being in ultrasonic non-destructive characterization, which is a very popular non-destructive characterization technique used in both industry, but really her focus when she went to go get her doctorate in mechanical engineering and applied mechanics at Nebraska Lincoln is focusing on heterogeneous media. And so when we think of how scattering an ultrasonic medium, it can be really simple with isotropic media where we have a very similar grain size. But once you start adding very complicated phases and other things that we want in today's modern composite materials, where we want all sorts of different requirements, it gets increasingly complicated. And so Dr. Argues' focus has been attacking all these different complicating scattering techniques in the wide variety of materials that we would like to ultrasonically characterize. And so she is a huge endorser of women in materials science and STEM in engineering science. Inside the Argues research group, we have diversity not only in our group, but also in areas of research where we will research in additive manufacturing, from cold sintering to new ways to ultrasonically characterize. There are so many different ways that we would like to apply our ultrasonic characterization into the world and allow this amazing technique to broaden. And so that's really our focus inside the group. In addition, she spends her time encouraging all of her students in her classes and in her lectures. She's been cited as one of the major promoters of material science and engineering science majors through her solids and dynamics classes, as well as a big promoter of women in STEM through their annual backpacking tours, which you can see here at the bottom right, of encouraging women to explore and travel along together to build a broader community and a really supportive community for women in STEM here at Penn State. And so that is why I nominated Dr. Argues.
Thanks. It's always nice to hear about some of our own. All right.
Hi, everyone. Thanks for joining today's webinar. I'll be talking about Stephanie Kolick, who was a scientist at DuPont Chemical Company. Just to start off with a little bit of background about Stephanie Kolick, she's actually a Pennsylvania native, and growing up, she really enjoyed exploring outdoors, collecting leaves, flowers, and making scrapbooks out of them and documenting her findings and observations. She also really enjoyed fabrics and sewing and creating clothing for her dolls. So clearly she was a really creative child. This led her into earning her degree in chemistry from the Carnegie Mellon University Women's College at the time. And here's where she developed her love for teaching, obviously chemistry, as well as her interest in medicine. So originally her plan was to join the medical field, but unfortunately, due to some financial hardships, she ended up going and working for the DuPont chemical company. And she loved it so much that she stayed there for her entire career. So she started off as a chemist and did a lot of work in low temperature processes for finding petroleum-based synthetic fibers. Over the course of her career, she earned 17 patents. And one of her most notable discoveries was the fabric known as Kevlar. So you can go to the next page now. So during her time, that led to her discovery of Kevlar, she was tasked with finding fibers that could withstand extreme conditions. So this included preparing intermediates, synthesizing aromatic polyamides of high molecular weight, and dissolving these polyamides in solvents, which would then be spun into fibers. So during her time, she ended up coming up with this cloudy solution that, after much convincing, she was able to get spun into the very strong and the strong fiber known as Kevlar. So Kevlar today has over 200 applications, one of the most important being bulletproof vests. But you can apply this across many industries. The aerospace industry, it's used in protective gear that you may wear, such as helmets and gloves, as well as sports equipment like tennis rackets. This also led to the development of many other fibers that are very common today. And an interesting fact about Stephanie is that she was actually the only person at DuPont who was involved in this level of research without her PhD, which speaks just to her intelligence and her dedication to learning. I think that here's some of her awards and notable mentions. So she was a mentor for other women scientists. So you can see a picture down on the bottom right here of her and her male colleagues. At the time, this was a very male-dominated field. So she always worked to support other women. She was also involved in many STEM outreach programs to children. One of her most notable demos was the nylon rope trick. And she was also nominated she was granted, I guess, a number of awards that were historically mainly granted to men. And she was also inducted into the Inventors Hall of Fame, as well as the National Women's Hall of Fame. So I think Stephanie is a great example of a female scientist who used her interests and her creativity and love for learning to really drive innovation during a challenging time for women in STEM. So that's why I wanted to highlight her today.
Thank you. That was really nice. All right.
Yes. So hi, everyone. For today's webinar, I thought I'd talk a bit about Judith Cohen, who was one of the first female aerospace engineers of America. So she was born on August 16, 1933 in Brooklyn, New York. And from a very young age, she got interested in mathematics because at that time, the only female role model for her who was basically doing anything interesting was her math teacher. And despite being counseled to go to a finishing school and get training to be a lady, she decided to go to college and learn maths, but then she fell in love with engineering. And then she later received her bachelor's and master's degrees from University of Southern California. And like during her time there, she never even met another female engineering student. And then she joined Space Technology Laboratories, which later became TRW, as an electrical engineer. And then while there too, she was often the only woman in the room. So about her achievements, the most important contribution of hers has to be credited with designing the abort guidance system that helped Apollo 13 crew members to navigate their way back to Earth when there was an oxygen tank explosion aboard the lunar the module, and then when the primary navigation system failed. Later on, she also, after she basically retired as an engineer, she also published a series, 11-book series called "You Can Be a Woman," that featured female professionals such as paleontologists, Egyptologists, and marine biologists to encourage young girls to get interested in STEM. Apart from that, she also worked on several other projects like the Minuteman missile. She also worked at the Science Ground Station for the Hubble Space Telescope, and as well as the tracking and data relay satellite. And finally, her legacy also lives through her children, two of whom are pretty popular. She's the mother of Neil Seigel, who's a computer scientist, systems engineer, and engineer, who has several contributions to science. He's credited with inventing the first. He's credited with inventing U.S. Army's first unmanned air vehicle system, and of course, her most popular, her most popular child has to be Jack Black, who's a Hollywood actor and comedian. Fun fact: on the day Jack Black was born, she was at her office, and she basically took out a printout of the problem she was working on, and at that time she was working on the abort guidance system. And then later on in the day, she called into our office and then basically said that I have solved this issue, and then also informed that she had given birth to Jack Black. So yeah, that's it.
All right, thank you, Arnam. And we'll go to our next one.
Hello, everyone. Please let me know if you cannot hear me. And thank you so much for joining today's webinar. And today I would like to introduce to Maysabel Leslie. She used to be a part of the Lord Ernst Rutherford group, research group. So, and next page, please. She born in Yorkshire in New England, and then received her chemistry from University of Leeds in 1908, and she had master degree from again University of Leeds with working with the Professor Harry Dawson, and worked on the iodinization of the acetone, and then published some of her work in the Transaction of the Chemistry Society. After her successful work in her master's degree, she got a scholarship to go to Radium Institute in Paris and had a chance to work with Madame Curie. And there she able to work in the thorium half-life. I mean, she did some characterization of the thorium half-life, its molecular weight, and then the products emanating from it. And she also published in French in her results in the Le Radium, again, Madame Curie's journal. And then after she completed her work with the Madame Curie. She moved back to the Manchester to work with the Lord Ernst Rutherford about, again, the thorium and then actinium, so with the similar work to working on their half-life of the radioactive products. After completing her work with the Ernst Rutherford, so during the World War I, she worked as a chemist in one of the government explosive agency as a head of that division. And because of her, successful work, she also promoted to be head of that government lab in the Liverpool. And then again, for instance, in University of Leeds, she got her doctoral degree in the thorium and explosive that she used to work in. They are based on the nitric acid, and she became a lecturer in the same department of the physical chemistry. And until her death, she kept working in the University of Leeds, and then in her obituary published in the Journal of Chemical Society, she had remarked with this words. She was the only woman in Leeds graduate who had been given a science doctorate. And then as a teacher, she always tried to open the roads for the students and then spare no effort to remove the difficulties encountered by the students to contact her. She was very accessible by her students. Next slide, please. And there were some remarks when I was doing the research I find very interesting, so that's why I want to share with you. When she was working with the Madame Curie in the Radium Institute, she had to work on the very large jars, including the thorium, a radioactive substance. At the time, they didn't know actually hazardous effect of the radioactivity, so that's why she was, when she was talking one of her mentors, she said that she had to air the room all the time and all because of the radioactivity that's in the room. She is exposed to that. And also, Ernst Rutherford accepted her application to the physical laboratory of the Victoria University of Manchester after he received a very positive letter from Madame Curie about Maysville Leslie, because she described her very serious and intelligent worker. And there was just one very unfortunate event in her life after she assigned as a head of the government lab in the Liverpool. Unfortunately, she lost her job when her male colleague come back from the World War I. Yeah, that at the time women wasn't really highly esteemed in their work. So it was one of the very unfortunate ones. Yeah, that's it. And thanks so much for listening.
Thanks for those insights. All right, we'll keep moving.
Hi, everyone, and thank you very much for this opportunity. Today, I wanted to share a bit about the life and legacy of Maria Gobert Meyer, a brilliant physicist who would be the second woman to win the Nobel Prize in Physics. She had quite a unique upbringing. She was born to a German family in Katowice, Prussia, which is now Katowice in Poland. Her father, a pediatrician, would soon receive a position at the University of Göttingen in central Germany. This was one of the most prestigious universities in the world at the time, and she would credit her father's scholarship and support of her ambitions for much of her inspiration later in life. Growing up, she was enrolled in a private school run by suffragettes to help prepare women for academia in Germany. And this was specifically with the goal of having those graduates establish more women's schools later in life. It would be with this support that she would successfully pass the university entrance exam a year earlier than her peers to become a student at the University of Göttingen. And this was when it was reaching the peak of its prestige, boasting the likes of Max Born, Hermann Weyl, and Edmund Landau among its faculty. So under the tutelage of Max Born, she would become a brilliant theoretical physicist, mainly studying quantum mechanics in its infancy. Within 6 years of entering university, she would produce her PhD thesis, which successfully predicted the two-photon absorption phenomenon 30 years before the first laser was developed, which allowed us to verify it experimentally and use it as an important imaging technique and microfabrication tool. This same year, she married Joseph Meyer, an American chemist who she would follow to the US. Next slide, please. In the US, she chose to stay with her husband, who received numerous appointments as professor at universities, including Johns Hopkins, Columbia, and the University of Chicago. Unfortunately, at the time, all these universities held strict nepotism laws. And while she was intent on continuing her work in physics, she was unable to secure for herself professional positions at any of these facilities. At Johns Hopkins, she was held equivalent to a graduate assistant, while at Columbia and Chicago, she held purely voluntary professor appointments, where she was granted access to the facilities there, but not given any salary. For periods of time, she would return to Germany to work with her previous advisors and became greatly focused on aiding refugee efforts in the 1930s, as many tried to flee following the rise of the Nazi Party. As a result of the work she produced in this time, she would come to be elected as a fellow of the American Physical Society prior to having been recognized as a full academic professor anywhere. With the onset of World War II, she would join the Manhattan Project to work on isotope properties and the behavior of materials under extreme conditions. Following the end of this work, she would become one of the founding group of scientists at Argonne National Lab, where she would still be limited to only a part-time appointment. In 1960, more than 30 years after the start of her career, she was hired as a full professor by the University of California, San Diego, where she would teach and perform research until her death. Next slide, please. Throughout her difficult career, Maria Gobert Meyer produced an incredible body of theoretical research. Her earlier work was focused on the foundations of quantum mechanics, following the environment she received her formal education in. As part of the Manhattan Project, she would develop methods for photochemical separation of isotopes, as well as many foundational models for the behavior of materials under extreme heat. As part of Argonne, she would produce her most famous result in the nuclear shell model, Similar to the concept of electron shells, Meyer developed a critical formulation of spin orbit coupling to explain which nuclei configurations would be stable. And it was this work that led to her Nobel Prize in Physics in 1963. Another outstanding accomplishment of hers was the programming of ENIAC, the very first programmable electronic computer as developed by the US Army to resolve a criticality problem for nuclear reactor design. She accomplished this using Monte Carlo methods in a time before computational simulation had really developed. And so this was a unique first-time achievement. Truly, in spite of the difficulties she faced, achieving recognition and professional support for nearly all her career, Maria Gobert-Meyer represented a scientist with absolute dedication and love for her craft. That's it for me. Thank you all for your time.
Thank you.
Hi, everyone. For today's webinar, I would like to share a female physics, Xin Zhao Wu, who is known as the First Lady of Physics, the Chinese Madame Curie, and the Queen of Nuclear Research, and etc. Wu was born in a small town in Taicang, which is very close to Shanghai. Her father was an engineer and her mother was a teacher. Her parents valued education very much and believed women and men were equal. They supported Wu to get an education just like her two brothers. In 1936, Wu came to the US for graduate study and later obtained her PhD in UC Berkeley. Next slide, please. She had many scientific achievements. In 1944, she joined the Manhattan Project, where her focus was on radiation detection. After World War II, she started investigating beta decay in Columbia University as an associate research professor, experimentally confirmed Fermi's theory of beta decay. She was named associate professor in 1952, making her the first woman who became a tenure track professor in Columbia. She also performed the famous parity experiment. So two theoretical physicists, Zheng Daoli and Zheng Yang, had the hypothesis that conservation of parity might not hold for weak nuclear reaction. And Wu experimentally proved this hypothesis was true, which resulted in Li and Yang receiving the 1957 Nobel Prize in Physics. But unfortunately, Wu was not acknowledged. In addition, she was also the first female president of American Physics Society. Next slide, please. So here I'm touching Wu's timeline that highlights her achievements. Feel free to read more about her and her work and her story if you're interested. Thank you.
All right, thank you.
Okay, hi, it's my turn. So I just realized that last year, Susan also introduced Yo-Yo. In the last year session, but I'm also it's kind of from another aspect to recognize Yo-Yo is very important, like a female scientist, especially she is the first female Asian to receive the Nobel Prize. So that is a really big achievement. So today I'd like to talk about her from my aspect. So Yo-Yo too, she was the Nobel Prize honor in the medicine in 2015. She was born in 1930 and in Zhejiang, Ningbo of China. And the reason why she got Nobel Prize is to recognize her discovery of finding a novel therapy against malaria. And the malaria is a very well spread a disease, which is widely located at a tropical climate region, especially in the South Asia and a lot of area of Africa. And many years ago, a lot of people suffer from this disease. So the new medicine discovery is very crucial for the human being health, and inspired by the traditional Chinese medicine. Previously, the Asian people, they use a sweet wormwood to treat the fever come from the malaria. And it turns out the active material is come from the artemisinin, and that is the active like a compound Yu has discovered and distilled to first time get the pure molecular and identify the structure of that. And so she not only successfully extract this like active material, but also develop some modified molecular structure inspired by this like natural structure to further enhance the effect of this medicine, which is commercialized broadly in nowadays like medicine, which will heal this malaria. So here you can see there is one picture like from her and her mentor in 1950s. I realized that the year she was doing the research, it is really tough year. So at that time when she was born, China is under the Second World War. So all of the conditions and the background is really not ideal for the research. And she is a female who is rooted from China and she educated from China. So I think it's really incredible achievement for her. And I also noticed that she only got a bachelor degree. So due to a lot of reasons, she don't have a chance to further get a higher degree. But what she has done did not like change. She's very focused on the project she is being assigned, and her heart is very kind and warm. And she said that she did research not for the award, but to benefit the whole human beings, because she's working on the medicine, and she hopes that the development of new medicine can benefit the whole human being society. So I think I'm really impressed by her personality and also the achievement she has done. So she's really like the role model of the female scientist, and we should follow. Yeah, thank you.
Thanks, Feifei. All right, so I have the last one here. So I wanted to highlight Ariana Rosenbluth, born Ariana Wright. And I have here the obituary that ran in the New York Times for her, which I thought was just really interesting. They listed her as a pioneering figure in data science, which is really interesting because she was a physicist. She never worked on data science, but her algorithms that she developed ended up being really important to machine learning. So essentially, she was an exceptional student. She received a PhD in physics at only 21. And she basically was really talented, not only in physics, but also you see here, there's a newspaper clipping here where she was competing in fencing competitively and actually qualified for the Olympics, but was not able to go to compete in the Olympics due to World War II. So let's see, we have here also a picture of her and her husband, Marshall Rosenbluth. And actually she has a little bit of a sad story in that she was a really bright rising star in this kind of computational physics, but really made all of her contributions in her 20s, and then left the field and really never pursued science again. This was largely due to social sort of forces at play at that time. Let's see. So this contribution basically is mostly having to do with this paper, which has Metropolis as the leading author. So, we refer to the algorithm now as the Metropolis Hastings algorithm, but, all of these people were on this paper. And actually, Dr. Rosenbluth implemented the Metropolis Hastings algorithms on this maniac supercomputer at Los Alamos. And so she was the first person to ever implement Markov chain Monte Carlo. And I made a note here that when I say implement, she was doing it in machine language because compilers were not yet available. And I think it's really interesting because I first was exposed to her work basically doing soft matter simulations and looking at polymer chains. So here in 1954, there's this paper by Rosenbluth and Rosenbluth. So her and her husband, Marshall, he basically was doing most of the math and she was doing the implementations on the computers. And so this is where I was exposed for the first time to her work. But she had a series of really important, influential papers in the 50s here. And then, yeah, sadly, never published again, even though she did spend later part of her life working on mathematics. I guess she was working on like knots and topology, but never published any of it. So yeah, a really influential person, despite having a very short scientific career. And with that, I want to hand it off for some closing remarks.
Hello, everyone, and thank you so much, Wes, for organizing this. Thank you all for your attention for these few minutes. I want to highlight some of the barriers faced by women in STEM today. So I know that a lot of talks like this focus on how we can encourage more women to get into STEM. And so I'll just talk a little bit about some of the pressures that women who are already there experience. I happen to have data about the US, but I imagine that a lot of these trends are global. Next slide, please. Okay, so the Scientific American did a pretty relevant piece recently. So I took a snippet from that, talking about the invisible forces that drive women in STEM out of the workforce. And I want to focus on specifically the traditional division of labor and gendered societal pressures, though there's a lot of overlap with all of the other issues as well. So a lot of people believe that academic women don't have as many kids. This is partially true, but actually that the trend is slowly becoming less and less true over time. So we see that the educational gap in motherhood is shrinking. So more and more women with PhDs are having kids to get up to the levels of the average population. And the point of this, I guess, is that this is a pretty common part of life for women. So most say that women do face a lot of pressure to be an involved parent. So we can see here that men face pressure, women face more pressure on the involved parent aspect, and then it's about inverted for the pressure to be successful in their job and career. So if this is what Americans were saying in 2017, this isn't just an old traditional problem, this is still currently the case. So let's see what happens over on the right when women and men who begin with full-time STEM employment. Let's see what happens to them when they have their first child. Over the course of 3 years, about 40%, a little over 40% of the mothers leave full-time STEM employment. But that is not true of the fathers. It's around 13% of the fathers leave full-time STEM employment. And then some amount of those even bounce back eventually, but that isn't true of the new mothers. So we lost almost half of all of these new mothers from the STEM workforce. So among US tenure track faculty, around 50% of the women have children compared to over 70% of the men, which makes this collection of plots here on the right a little more staggering in my opinion. This is really part of a broader issue in our current society that is evidenced by there's a lot of research on this issue, which is summarized by a growing body of evidence suggests that employers reward men for being fathers and penalize women for being mothers. I don't have time to get into all the details of this. I have sources for this in the captions of the presentation if anyone is interested. Next slide, please. Thank you. Okay, and so in the top left here, we have some data from the US Bureau of Labor Statistics about the average hours per week spent doing unpaid and paid work separated by sex. And we see that women and men total actually work around the same number of hours total. Women work even slightly more, but it's marginal. that's for the average population. Over on the right, we have information about women and men scientists and the division of labor in their homes versus the hours that they work per week. And what we see actually is that the average woman scientist works a pretty similar distribution of hours, paid hours in the bottom right to men. However, we see in the top right that these women scientists are doing statistically more of their unpaid household labor than the men scientists. So actually, if you put this information together, the women scientists are getting a much better or a much worse deal of this than the average man or woman in the United States. Thank you for your time.
All right, thanks for those thoughts. I think we saw this theme running throughout actually several hundred years of the presentations we heard today. So this is really important to be cognizant of. That's all the programming that we have today. So thank you for attending, and this recording will be posted online if you'd like to review it later.